Hi there. So I was just working on some experiments and I ran into a performance problem that I thought might be worth sharing. Threw together a quick presentation and the title is NUMA Memory Placement Matters. So the experimental machine that I'm working on here is a 4-socket machine. It has 4 Intel Xeon 6150 Gold processors. They are physical chips that go into a board that looks something like this on the right. So there are 4 separate sockets. Each socket has 18 cores and 36 threads with hyperthreading. So in total, we got 72 cores and 144 threads. We have 512 gigs of RAM, and some of that RAM is local to each socket. So you can kind of see this in the motherboard itself. You have a socket, then you have some RAM banks next to it. So each of these sockets has a bunch of RAM banks that are sort of local to that socket. And if you access those RAM banks, it's a little bit cheaper. And if you access RAM banks local to another socket, you pay some performance penalty to access them. So what's the problem that I'm running into? Well, what I'm trying to do is implement maximal independent set, a graph algorithm on, for the purposes of this talk, let's just think of it as a random like GNP graph with 10 million nodes and 100 million edges. And I'm comparing 2 different solutions, a concurrent solution and a sequential implementation. And the methodology is I'm going to build a graph, a random graph, with 144 threads saturating the whole system, and I'm doing this just for speed. Really, I'm not actually interested in small graphs with 10 million nodes and 100 million edges. I'm actually interested in like 10 billion, 50 billion edge graphs, which are much larger, and it can be really prohibitively expensive to build these graphs with a single thread. So, if it takes sort of 5 minutes or so to build one of these graphs with 144 threads, my experimental setup would be, totally unrunnable. If there's no way I'd be able to get enough CPU time to, reasonably run these things and iterate on the results if I had to build them with 1 thread. So I want to build my graphs with 144 threads, even though I sometimes want to run just a single thread in the measured experimental portion of my runs. So I'm building the graph, and then I'm trying to compare these, 2 solutions. First, looking at kind of the overhead of concurrency in the concurrent solution. So I want to compare the single-threaded sequential implementation, like an optimized sequential implementation of MIS, greedy MIS, with our concurrent implementation running with just a single thread. And this will sort of give us some idea how much overhead do we add by throwing in all this synchronization machinery to make concurrent execution safe. And then we also kind of want to think about the scaling. So how much does our concurrent implementation improve performance? And when you do this, of course, I don't want to compare against my own concurrent implementation at a single thread and sort of see how that scales. I really want to compare how my solution scales versus like an optimized sequential algorithm, because that's how you figure out whether you've actually made progress in a problem, as you compare to the best sequential algorithm, not to the single-threaded concurrent implementation, which has a lot of overhead compared to the sequential algorithm. So we want to compare 1-thread sequential versus 144 threads concurrent. So if I run some experiments like this and show you the results, here are some bad results. This is the running time in seconds to solve an instance of MIS on a random graph. The sequential algorithm takes about 2.9 seconds. The concurrent algorithm with a single thread takes about 3.5 seconds. There's some overhead there. And the concurrent algorithm with 144 threads takes about 0.125 seconds. So this is apparently a 23 times speed up, which sounds really great. But I didn't stop here. I dug a little bit deeper to try to understand these results, and eventually I realized that the sequential algorithm should probably be a lot faster compared to the concurrent algorithm. Well, the way I got there is I dug around in all sorts of performance counters and things like that, but the way I'm going to present it to you is sort of what was the problem and what's the solution. So what is the NUMA memory placement of the graph in each of these cases? Well, the graph is being initialized with 144 threads. And by default, threads tend to allocate memory wherever they're running. So if a thread's running on socket 2, when it allocates memory, it's probably going to allocate pages that are local to socket 2. Threads running on all sockets in our initialization means that memory is allocated on all sockets in our initialization. So it looks something like this diagram on the right, where we have 4 sockets and about a quarter of the memory is allocated on each socket. And this is great if we're running with lots of threads, but in a single-threaded run, this means only about a quarter of the memory is local to the socket where that single thread is running. And this is not terribly realistic because in a real sequential execution where you're building the graph with a single thread also, all of the memory is going to be local to the socket where that thread's running. And so initialization is really creating a performance problem here, because it's scattering the memory across all of the sockets and causing the single-threaded measured portion of the execution to incur lots of extra, penalties as it has to access, 3 out of 4 times memory that's not local to the socket it's running on. That's a problem. How can we fix that? Well, you can control memory placement in a NUMA system by using this wonderful utility called NUMA-CTL. This is actually their logo, which I thought was kind of cute. So how do we configure the system to have proper memory placement for a single-threaded run? Well, we want to initialize with 144 threads still, but we want to allocate memory only on one socket. And so we can just prefix our command with NUMA-CTL-I0, and this means allocate memory only on socket 0. So what does this look like in practice? I like to show stuff kind of live to see what it's like. So here's a command that I'm running to generate some numbers. This is I'm starting off with this LD preload, which is replacing the standard glibc allocator, malloc, with a faster, more scalable allocator called jemalloc. I'm just prepending my command with that to do that sort of live swap of the malloc function's implementation. And then I'm calling my actual binary file, qbench sequential. This is the sequential implementation of MIS, and I have a whole bunch of arguments here that you don't have to worry about. What I'm going to do is I'm going to run this first, just sort of vanilla, and see what comes out. So this is the sequential execution, and it ran in about 2.67 seconds. Now I'm going to throw NUMA-CTL in there. So this is NUMA-CTL-I saying interleave the pages that are allocated between these NUMA nodes, only 0. So allocate all the pages on NUMA node 0, and that's where that one thread is going to be running. I'm pinning that thread to run on socket 0. When I run that, how does that affect performance? Well, we can see that the trial ends after 1.76 seconds. You get a really appreciable performance improvement by actually pinning threads to, well, this one thread to the single socket and pinning all of the allocated memory also to that socket. We're still allocating memory with 144 threads running on 4 different sockets, but they're all allocating it on the first socket. So that's nice. We actually get that local placement. Okay. So how does that affect our results? I mean, I showed you a small improvement there, but I can show you, here I have actually averages of many runs. So you have a little bit more statistical, rigor. So these results are still bad. I'll explain why. So at the top, we have allocating on a single socket using NUMA-CTL-I0. And below, we have the default memory placement, which was really to use all sockets. So the sequential algorithms improved from 2.9 seconds to 1.85, the concurrent single-threaded from 3.5 to 2.3. These are nice improvements. So the single-threaded runs, we're getting really nice improvements by binding memory to a single socket. But the concurrent 144-thread execution has gotten a lot worse, almost twice as bad. So that's not great. Why did the 144-thread execution get slower? Well, of course, NUMA-CTL-I0 causes all memory to be local to socket 0, and for single-threaded executions, that means all memory is local, which is great. But for 144-thread execution, that means all threads are hammering the local memory of one socket, which is not so good. So what this means is there isn't one, one-size-fits-all memory placement scheme for all different thread counts. The proper NUMA memory placement scheme is going to be different for different thread counts. So for a single-threaded execution, you really want single-socket allocation, but for a 144-thread execution, allocation on all sockets is best. And of course, with 144 threads, our initialization thread count of 144 matches the thread count we're running in the the measured part of our experiment. So actually, the default behavior of letting threads allocate memory wherever they're running is correct. And so we can just use no NUMA-CTL, or we can use NUMA-CTL-I all, which interleaves the pages round robin as they're allocated across all of the sockets or NUMA nodes. And so how do we get realistic results? Well, we have to run allocations on a single socket for sequential and concurrent single-threaded, And we have to run sort of the default memory placement where we use all sockets for the concurrent 144 thread run. And if we take those numbers, we end up with a nice, reasonable 15x speed up for 144 threads over the optimized sequential algorithm. Okay, so what if we're not running these easy thread counts like 1 or 144 where it's really obvious what to do? What if we run 36 threads or 72 or 84? So if we run 36 threads, remember on our system we have 36 threads per socket, that's exactly one socket full of threads, so it's pretty obvious what to do. We should use NUMA-CTL-I0. All the memory should be allocated on that single socket. If we run 72 threads, then there are exactly two sockets full of threads, so you should be using NUMA-CTL-I0, 1. This is of course assuming that we're pinning threads so that they run on these sockets only. With 84 threads, it's a little harder. This is sort of a tricky case because 84 threads is two full sockets of threads, 72 threads, plus 12 more threads. So sort of a third of a third socket, 12 out of 36 threads running on socket 2. So we could use NUMA-CTL-I0, 1, 2. Then NUMA-CTL will evenly distribute memory between the three sockets. So a third of the memory will be local to socket 0, a third will be local to socket 1, and a third will be local to socket 2. But threads are not evenly distributed between those three sockets. So socket 2 is only running 12 threads compared to 36 on socket 0 and 36 on socket 1. And so what ends up happening is these threads have a disproportionately large amount of local memory on socket 2. A third of the memory is local there when a small fraction of the threads are running there. And that's obviously not optimal if you want to maximize the aggregate performance of all threads. Really, more of the memory should be local to sockets 0 and 1 than to socket 2, and that'll improve sort of the average performance of all threads. And so the best solution in this case is to initialize the graph or the data structure or whatever you're working on with exactly 84 threads. So the number of threads in initialization should exactly match the number of threads in the measured portion of the experiment. Now what will that result in? Well, then the memory local to socket 2 will be proportional to the number of threads running there, assuming that during initialization all threads allocate roughly the same amount of memory. So we'll have 36 out of 84 fraction of the memory that's local to socket 0, 36 out of 84 fraction of the memory that's local to socket 1, and 12 out of 84 fraction of the memory that's local to socket 2. Okay, so what's the take-home message? If you're initializing low thread count experiments, like you have a measured part of your experiment with a low thread count, but you're using large thread counts to initialize your data structures, then that can change your results substantially. And if you want to avoid those kinds of weird problems in your experiments, then you should either initialize with the same number of threads as you're going to run in the measured part of the experiment, if that's feasible, and of course pin threads so that they're running on the same cores in each case. In the initialization part of your program and in the measured part of your program, they should be running on the same sockets and the same cores, ideally. Or B, use NUMA-CTL to restrict memory placement. And if you want to use NUMA-CTL appropriately, then if all of your threads fit on one socket, use NUMA-CTL-I0, that's easy. Beyond one socket, to avoid problems that we saw with weird thread counts like 84, you should probably only run thread counts that fill up entire sockets. So on our system, that would be 72, 108, and 144, multiples of 36, the thread count that fills up a socket. And then you're going to use NUMA-CTL-I01, 012 or 0123 as appropriate. Okay, so hope you enjoyed that and learned something. I'll leave it off there, and thanks for watching. I'll see you next time.